Okie dokie. So I don't see any new attendees tonight, so I'll skip the usual intro spiel. Welcome back, everybody. So this month for AFSIG, we are going to be following up on a presentation that Pete did in April about multi-messenger astronomy. And there were some questions which were brought up regarding gravitational waves and some ambiguity around those, which I wanted to go in a little bit more and try to get some better answers on, since I, I felt that our answers weren't very satisfactory on that call, and uh, and try to give more light onto those because it is a complex topic. And there we go. So this presentation is going to basically give a little bit of a more introduction and try to give at least a foundational knowledge of what gravitational waves actually are. And then we'll spend most of the rest of this presentation talking about the history and development of gravitational waves, both from concept into actual physical observations. And then briefly touch about on I have like more of an open floor discussion because I didn't actually get to finish all this because this was getting to be a really long presentation. So discoveries actually I should have removed, but we're not going to talk about those tonight. Unfortunately, there's probably too much content in this already, which is rare for me to say in a presentation. There's a lot to go here. So starting with the obvious question of what are they? So as many of us are familiar with, at least for those who are following a lot of science, general relativity and Einstein, which I think most people are familiar with within astronomy circles, is that its main prediction that actually made it detectable was that heavy objects bend space. Space and time are inseparable for each other, and mass and time interact as one entity. And when it comes to this bending effect, this is often described as you take a ball and you put it into a sheet fabric and you pull the fabric taut. You'll see that that ball will still pull down into the fabric, bending it. This is just now a way that you can more easily visualize just the bending of space, where the sheet itself is space. And in gravity, so from there, if you start adding more and more objects to this sheet, you'll start creating more and more of these little dimples all around it. And so we start with this by, taking two objects on this sheet, and then we start spinning them around each other. This will all make sense here as we go on. And so as these two objects move around these sheets, you'll see that, like how you would put a thing on your bed, it's going to leave behind a little wake that will, deform with the ball's travel and then remerge with the sheet behind it as they move. Clear so far? So these movements or ripples are in effect what gravity waves are, and this motion of these objects through space is causing this entire sheet to vibrate. And we'll elaborate more on this on here in a second. So this is a slightly an animated GIF showing that in a little bit more detail, where the blue here is the actual sheet fabric, and we have these two balls inside that are pushing around the sheet and deforming it. And as you can see, we have these really high peaks here in the center. And as they get farther and farther away, they lower their amplitude and they start merging back in with the sheet all together. So building on that, we started with these two balls that are creating ripples in this sheet. And these, you can picture these as vibrations. If you were to swap this analogy more, you go from, instead of being through space, you have two ringing balls that you struck together on a steel beam, and that steel beam is vibrating rapidly. So those two balls are still representing that mass that we originally started with. the steel beam now becoming a substitute for space. And so these collision of these two balls against the steel beam are creating a ringing effect, which is what we ourselves would hear. And in this analogy, that ringing combined with the actual oscillations of the beam, because as you know, within normal sound, that's actually a vibration that's translated through a surface, which is what we manifest as sound. In this case, the ringing itself and the vibration are gravity waves. So, uh, so oh, you. So, and as a consequence of this, which is a minor detail, which well, not just a minor, which is the key detail, but still worth noting. When we take these two massive objects and merge them together, which is the primary manifestation, the primary mechanism that has created the gravity waves we've been able to detect to date, their combined mass, like all process, this isn't a perfect process. The law of conservation energy still applies. And so during this merger of two objects, their masses will become one, but then some of that mass will be converted directly into gravitational wave energy. That's just a little small segue over here, but worth noting nonetheless. It'll come back. We'll come back to that object way at the end of the presentation. So another way that you can visualize this effect is still going back kind of roughly into the sheet analogy, but I felt coming into this with more visualizations, because some people grasp the different ones differently, is that you start with a very a calm lake surface, and as I like putting random jokes occasionally. For all of you physics students, you're dealing with a frozen, fictionless lake in a vacuum. We get to ignore friction and drag and all that other fun stuff. So we have the surface of a lake. It's very calm. It's still fluid. And we're going to scatter a whole bunch of debris around it, in the form of leaves, twigs, pieces of bird feathers, whatever have you, that you would normally go out and when you're walking and you find a lake and you just see a whole bunch of stuff on it. So as as we know, you put something on top of something of water, or really any water-based fluid, we have surface tension to contend with, and so an object will start to deform the surface of the lake slightly where it touches to, just because the water surface tension is just preventing that object from sinking. Yeah, for everyone going back into our good friend Cheerios that all physicists love to play with. This is very much the same thing, as that the surface tension of the fluid just keeps the surface about. And so as you start moving these pieces of debris across the lake, by whatever means they have you, they're also leaving ripples in the water that will travel across each other. And those ripples will then start intersecting with other pieces of debris, with larger pieces resulting in larger ripples. So same general concept here on all of this. It's just some piece of mass causes a ripple through some medium that we ultimately detect. But what's different from gravity waves is, with that, normally we're used to like, oh yeah, hey, photons, hey, light, they're waves, sort of. It's kind of a complex argument there. But in most discussions of radiation that we will come across, there's always weird things with advanced physics where somebody does something with some weird thing of radiation. But for the normal ones that we're quote unquote exposed to on a daily basis, you have the big ones of alpha radiation, beta radiation, neutron radiation, and your electromagnetic radiation. Those are like the core radiations that manifest in terms of like the foundational radiation. You have other things like heat radiation and other stuff, but those are ultimately components of one or more of these other basic types. So these all originate from some fundamental force carrying particle or particles. They are tied back to, whether it be an electron, a photon, or in the case of alpha and beta, you have a neutron, a neutron particle, or a helium nucleus is also for beta radiation. So there's some form of matter that underpins these other forms of radiation. Gravitational waves are not carried by any particle. What separates them is that they are oscillations in space and time itself. So that's part of the thing that makes them so tricky to detect, is that you're not trying to, you're having to basically observe to see if space itself changes in a way that you can't see. You can't actually say like, oh yeah, is there more stuff in this room? Is there more gases there? Is there a physical manifestation on it in terms of like pressure or volume or temperature? You can't do any of that. And you can't rely on, looking at gravitational disturbances directly, because at least, when we in astronomy talk about gravitational disturbance, we're talking about really, really heavy things like stars or planets. And these signals are so unbelievably weak that you can't rely on those classical mechanisms of detection either. So we had to go and get creative. And we'll talk more about exactly how we got creative later in this. Questions or comments before I move on to talking about a lot of the history behind this? Cool. So where did we go in order to get here? That was kind of like the big thing. And also something that, when we also talk about gravity, we're just like, oh yeah, Einstein, he did this thing. And, a lot of things themselves kind of get contributed to Einstein, I think, which in this case is certainly true. But then also other phenomena later be like, oh yeah, Einstein general relativity predicted X. So they get attributed to Einstein, but sometimes it's really just more like, hey, we played around with general relativity a lot over the last 100 years, and as people did more math on it, we found some really weird things. So there's the two sides of discovery on this. Unfortunately, this is one of those that's like, no, Einstein really did predict some of this, rather than people who came after it in the study of general relativity. But before we can get to general relativity, we can first go back to where the first sort of mention of gravitational waves comes from, which, at least in the sources I found, which I don't think you'll find this on Wikipedia. I actually had to find this in a couple of archive papers, which is where most of this content comes from. They're really good papers. I'll post links to them after this. They're worth the read. They're not very, well, one sort of math heavy, but you could skip all the math. So circling back, we start with a British mathematician and philosopher who named William Kingdon Clifford in 1876. And he was writing in one of his books that, quote, small portions of space are in fact of a nature analogous to little hills on a surface, which is on average flat. That sounds familiar. Namely, that the ordinary laws of geometry are not valid for them. That the property of being curved or distorted is continually being passed on from one portion of space to another after the manner of a wave. That this variation of the curvature of space is what really happens in that phenomenon which we call the motion of matter, whether ponderable or ethereal. So, not necessarily using gravitational waves by name in this, but this paragraph contains a lot of things that, with the historical hindsight we have, seem very familiar. You have the curvature of space-time being discussed here, gravitational waves being propagated out through motion, and all that, him trying to relate this back to Newton's theory of gravity. All of this in 1876. From there, we go and leap forward about another 30 years, and we jump to Henry Poincare. He is, at the current time, this is always one of those things, is like history changes and we find things. But he is currently the one credited with actually naming gravitational waves in one of his papers from 1905 called On the Dynamics of the Electron. In this paper, he assumed that the gravitational force propagates at the speed of light. And based on this idea, through a couple of other hoops, he reached to the point where he concluded that a change in gravity and its manifesting effect will propagate out like a wave, simply because it's bounded by the speed of light. It's not, you have locality, and so it's essentially you have this ripple and it's propagating out, and so there, and yeah, that's how he reached this. And he specifically just termed this gravitational waves. Uh, and one of the ironies of history, this paper also set out a lot of the ideas that were found in general relativity later from Einstein. But there were math errors and other mathematical foundations that were lacking in this. And so while it had a lot of the concepts, the the physical foundations of it were inadequate. And so it was sort of just kicked to the can, and Einstein kind of gets all the credit. But at least in the paper that I described this like, yeah, though this was basically a first stab at general relativity that just unfortunately didn't have the right math behind it to give it the credit that it wanted. After Poincare's first actual mention of gravity waves, we leap forward into the era of general relativity, with Einstein publishing his paper in 1915. And shortly after that, we have the exchange between Einstein and Charles Schwarzschild, where Schwarz was like, "Hey, I found black holes." Einstein's like, I don't like those. That can't happen." And we kind of all know, some of us, some of my other talks where I've talked about this relationship with Schwarzschild and black holes, we kind of know where that went. And in this exchange, Einstein wrote to Charles essentially, yeah, no, there's no such thing as gravitational waves. They're not analogous to light waves, which in hindsight is technically true, as we just discussed. Gravitational waves are not analogous to light waves in the classical sense, at least of how we physically define them. So score one for Einstein by being wrong but being right. And uh, later in this exchange, he would go and change his mind, as he often did as he worked through this really complex theory of his. And he would have a correspondence with physicist William de Sitter, who is also a really big name in physics at the time, especially in cosmology and in the formation of the universe. And they were working on, Einstein was working at the time at some fine to general relativity, and he would go like, yeah, maybe they kind of sort of do exist, maybe they don't. He would change his mind a couple of times and go back and forth on this. And part of this decision goes into a concept which, um, him trying to relate gravity waves to magnetism. With magnetism, you have this north-south, you have this what's known as a dipole behavior. And very loosely glossing over this because I couldn't really understand what this meant, is gravity waves originate from what's known as a quadrupole. Don't ask me what that is. I still need to kind of wrap my head around what that is and what that means and how it physically amounts, because it's some of it's like this is a physics thing versus an actual manifest thing, so it gets a little bit weird. So just know that that term exists. It's interesting. I'll probably look at it more. But that sort of discrepancy. So as he worked through most of 1916, he would publish a couple of things, and he would go on to publish a paper in 1918 called "On Gravitational Waves," where he would dig into this a little bit more about whether or not they exist. I think I actually talked about this paper again. No, where he could have just like was saying, "Oh yeah, they may exist, but they might not," in this flip flop of various papers. And so over the next 2 decades, Einstein, Eddington, and other big names in physics at this time would have this like, well, do they exist? Do they don't? Kind of warring, dueling press releases with each other. In some of the papers that Einstein would write, Eddington was able to go in and say like, well, hey, some of your stuff really depends on your reference frame, which is basically where you put your observer, and so we could make gravity waves that travel instantaneously, which would lead to one of Einstein's quotes of quote for traveling at the speed of thought. So sorting out the mathematics of this was a very complicated endeavor. which led to a lot of adding more to the confusion of do they exist, do they not exist, or are they just some math quirk? So as we move out of that 20-year period of finding out whether or not gravity waves exist, we move on to another paper which Einstein collaborated on with physicist Nathan Rosen. For those who recognize that name with the Einstein-Rosen bridge and Einstein-Rosen rings, so this is the same Rosen attached to those big name topics. And in this paper that they titled "Do Gravity Waves Exist?" they concluded, yeah, no, they don't. And Einstein, they sent this off for peer review, to publication. And during this publication, the publisher that Einstein sent it to was adding in this process, and they sent the paper off to an anonymous reviewer. So this was, which was a process that Einstein himself wasn't familiar with through the German publications that he had historically gone through. And so part of this stems from this particular publication published something from Einstein's that Einstein originally retracted, and so they wanted to have just to publish it on blind faith, and so they wanted to have to avoid that retraction this time, and would send this paper off to an anonymous reviewer just for a second look at, and this made Einstein really upset, and just because he had not. This was still in the hyper-competitive phases of academia and professional research. And I was like, I don't want somebody stealing out my ideas from behind me or taking credit for my work sort of mentality that is still prevalent today in certain academic circles. But he got really mad at this publisher and vowed never to publish there again. And he never actually did. But this peer reviewer did find errors, and they did try to tell Einstein about them, but Einstein was just in his fury. He was like, no, I'm not going to look at this. And so those errors were sort of brushed aside. Just because we've had lots of falls of text, I need to introduce random pictures in here at a time. So this is a picture of Albert Einstein and Nathan Rosen together at some point in the 1930s, I believe. So we had this paper that was about to be published by Einstein talking about, hey, gravity waves don't exist. But then, during this long lull, Einstein was working of this publication process. Nathan Rosen had moved on from Einstein and had moved into Russia. And so Einstein began working with a new assistant called Leopold Enfield. And during a course of random events, Leopold Enfield was invited by a person named H.P. Robertson, and the pair sort of struck up a collaboration/friendship. And Enfield would then began discussing with Robertson all of the work that Einstein had been doing, that the pair, Einstein and himself, had been doing along gravity waves, and they started talking about this paper. And one thing led to another, and the pair got looking more at the paper, and Robertson managed to find the errors, find those same errors again. And they politely told Einstein about them this time. And since they were taken from his own assistants, he was a little bit more curious about them and actually went to go and address them. And these errors ultimately led Einstein to the exact opposite conclusion of the original publication. And he was slated to give a talk on this original paper the very next day for the first time. And so over the course of 12 hours, he had to completely rewrite his presentation and his talk. And this fury of academia of last minute rewriting, which I find hilarious. And so, recognizing that this was sort of like a hasty rewrite, rather than fully delving into this or not, as he ended this talk, he skirted the issue of it altogether by just saying, quote, if you ask me whether there are gravitational waves or not, I must answer, I do not know, but it is a highly interesting problem. And so, in his app, once that presentation was given, they went back more on working and fixing the errors in general. And this was eventually then republished again as a paper on gravitational waves, and which concluded we investigate rigorously the cause of cylindrical gravitational waves, it turns out that rigorous solutions exist and that the problem reduces to blah, blah, blah. So this is Einstein saying that a specific type of gravity waves exist. There may be others. And a curiosity that was later I found during this paper is it wasn't actually found until the 21st century that Robertson, uh, sort of who helped find the errors, was actually the original anonymous reviewer in the first place. And so this was sort of like, it feels like this was one of those like sneaky sort of like, well, this is a pretty serious thing. I should probably go help out here, as sort of just like him trying to push Einstein to get himself corrected. So it's almost like, you know, a back end just person just nudging you towards the solution that you wanted sort of event. Which is very curious as to why Robertson did the things that he did after getting that retraction from Einstein. So, even after this publication where Einstein sort of admits like, yeah, they exist, this debate would continue very well into the 80s on whether or not they exist, and so various refinements about what the properties of gravity waves are, what sort of types there are, how do we actually detect them, blah, and all the other good stuff, once you have some foundational theory. So now we're moving out of the theoretical background of like, okay, we go from general relativity to gravity waves and the theoretical aspects, and we can go more into the observational paradigms of this. Obviously, we have theory that's still going on. You can't really escape the two, but now we can get into the actual fun stuff of going out and trying to build massive things. Because everyone likes building massive detectors, right? Let's go throw billions of dollars at things, because why not? So we skip ahead a bit into 1957. And we start at what becomes known as the Chapel Hill Conference, or the first Chapel Hill Conference, which occurs in Chapel Hill, North Carolina. This was a 6-day conference that was invite only to a lot of specific physicists at the time. And this 6-day conference held the title Conference on the Role of Gravitation in Physics. Unfortunately for us, Albert Einstein died 8 months prior to this conference, so he was absent from this meeting for obvious reasons. But there are a lot of other subtle names here, some of which I didn't recognize, but other topics from this, which would come out of this very first conference, was the first discussion of the many worlds interpretation. Hey, who likes our parallel universes? Raise your hand. That was where that was first debated here. The quantum gravity and gravitational waves were debated, and in this conference, the term wormholes was first coined. So a lot of interesting things happened here at Chapel Hill. And the main thing for our purposes of discussion is that this conference will go about kicking off the modern hunt for gravitational waves, and got people actually out of the theory aspects and trying to figure out, okay, how do we detect them? And for that, we jump to Joseph Weber. He was one of the physicists who attended Chapel Hill, who was conveniently on sabbatical at the time. One of the more interesting things is that Weber is known for is he provided some of the theoretical work that would go on to define the maser and later the laser. So he's not the actual inventor of the laser, but he did some the theoretical foundations that led to their development. So interesting name there. And he came out of Chapel Hill and was just like, I'm going to build a detector for this. And so after Chapel Hill, he would go on and spend 3 years thinking of ways to detect gravitational waves, publishing a technical approach for how to do this in 1959, and then going out and building his first detector in 1966. This device, this detector of his, consisted of a 7,000-pound aluminum cylinder that was wrapped in detectors and suspended by a wire. And this specific form of detector was the primary type used for various gravitational wave experiences for a good while at various scales, and is specifically referred to as a bar detector. And in his experimental setup, he built these 2 giant hulking pieces of aluminum, and he separated them by about 400 miles so that he could potentially isolate issues with local noise. Some of the things that we see today, space 2 things really far apart, see if they have the same event. If it's not, great, publish. And he built detectors that would spend 3 years collecting data, and he would publish his results in 1969. saying, "Hey, I found gravitational waves." People were obviously skeptical about this, and they would dive into his results, and over a couple of years would hash out like, "Nah, your stuff's just background noise, not really there," and the subject of coincidence. But nonetheless, people were intrigued, and they would build variations of his detector at other scales, locations, and sizes, and changing some of the ways about how the detectors worked, and to try to like say, "Oh, well, this seems like a valid approach. Let's just see if we can get something out of it." And each of these detectors would go on show no real detections. And at some point, I wasn't able to determine when um, it was found that these detectors have a fundamental detection range limit of the 100 to 900 hertz range, which is audible sound. So they could really only detect audible sound. Which when you think about that for a second, it's like, but you can't hear gravity waves. So if you could, you'd be hearing ringing in your ears all the time from all the black hole mergers going off in space. You know, so regardless of that, we eventually found out that some other approach was needed in terms of building a physical detector for this. So this is both a diagram and an image of Weber's original detector. You have this giant cylinder wrapped in a whole bunch of individual detector plates and 1970s technology, and then it's hung from this bar suspended by the roof. Great. Nothing too fancy there, although it looks sort of fancy. So, as Weber worked through, as the physics community at large worked through their, detections and other objects and how to build, crazy scientific instruments in order to justify their PhDs and research grants. We skip ahead into 1974, where the binary pulsar PSR 1913 plus 16 was discovered, and which would also go on to earn its two discoverers a Nobel Prize, not in physics. But after this discovery, the original observers of this binary pulsar pair kept watching it, and as they took more and more observations of this binary pulsar, they found that its orbit was decaying, inconsistent with key observations of general relativity and how those, and which specifically were related to effects of gravity waves. And so, okay, great. We found something observational in the sky that matches what we would expect from gravity waves. So cool. That's a good, strong sign that they probably exist, and we're not chasing red herrings. And over the course of the next 30 years, we would keep watching this binary pulsar just to see if anything about it has changed in case general relativity decides to throw a fast one on us, or the universe does. So far, this observation has held up. And so this orbital decay of these two binary pulsars is very strong evidence. Granted, it's not like Eureka, this exists in terms of physics standpoint, but it does provide a very strong indirect confirmation of gravitational waves. And so we skip ahead through a whole, 2 decades after 1976. We go into the land of interferometries, and that sort of thing. Actually, no, sorry, I'm jumping ahead. So we jumping from 1976 back to 1962. We find out that there's two Russian physicists. Gershenstein is, I'm pretty sure, a German name, so that's probably one of those expatriated Nazi scientists that Russia took from World War II. As certainly we did. But these two scientists are the first actually credit of using what's known as interferometers in order to detect gravity waves. And Weber himself, with his bar detector, actually also considered these independently, but didn't really come into this approach, which led to his bar detector. Although one of his collaborators, Robert Forward, would go on to actually build an interferometer for gravitational waves. But sadly, his detector was way too small to be able to make much detection. And the Western world was actually unaware of Pustovitz's and Gerstenstein's discovery because it was only published in an inaccessible Soviet journal, and a lot of Soviet science was cut off from the Western world during the Cold War era. And so we're still finding things from Soviet papers today and tracing things back. So, but regardless, we were working through the 70s as well as these bar detectors, and so others were working on how can we make interferometers practical for this purpose, but overall limited by the fundamental technologies of their day. Obviously technology has come a very long way since 1970. So, and with that, we can jump squarely into the world of LIGO and Virgo. So moving forward into the 90s, we have all the main things that come out in the 90s. We have the internet, more powerful supercomputers, cheaper supercomputers, and it became a lot more practical for institutions to try to build large-scale interferometers, especially with structural engineering techniques that have improved. But the main things with any interferometer for gravitational waves is, we'll talk more about the work in a second, but just to call out some of this, they need to be sensitive to a change in amplitude of light. They primarily work by analyzing light waves, and of a precision of 10 to the 16. So they need to be able to detect a change in light that's smaller than the width of a proton, which is where this information, that some may have heard this analogy, but it's very true. So this sheer sensitivity of having to be the 10 to the minus 16 in precision, which is 10 with 16 zeros after it in a decimal place, is where the minus comes in. As that this is very subtle and exposed to noise signals, various sources of the noise. As the picture on the right shows, you have noise from the laser output, noise from light itself, mechanical thermal noise in your mirrors and your antennas and your detectors, other radiation from the laser, seismic noise, heat, cosmic rays, and just general great gravity background and other stuff. So there's a whole bunch of noise that we have to sort of figure out what to do with, which was why I said what this took so long. There's just a lot of things to have to consider. And so the way this works in an interferometer, at least a gravitational wave interferometer, which is specifically known as a dual arm interferometer or a long arm interferometer, is that you take this laser and you shine it down a beam splitter, which splits the laser in two. And then you shine those two pieces of the laser down very, very long tunnels. In the case of LIGO and Virgo instruments, those tunnels are 3 kilometers and 4 kilometers respectively. And these beams, lasers, will be sent through a couple of mirrors along the way and bounce back from one end of the tunnel back to the beam splitter, which is sitting next to a detector itself, and so that they can analyze it. The key thing about this arrangement, why it's important, is that these mirrors need to be separated from each other at right angles. This is specifically dealing with a specific property of gravitational waves, which I don't want to get into. It's complicated. So the idea being with this is that gravity waves will pass through the facility, distorting space and time and causing the mirror's positions to shift, the actual physical mirrors to shift ever so slightly. So this shift alters the phase of the lasers as they travel back to the beam splitter in a way that can be physically measured. So it's like, if you start playing sound on 2 record players at once, and then you bump the table on like one of the old turntables tables to bump the needle, and it jumps ahead a little bit by 2 seconds. That's sort of the same basic principle here of what we're trying to measure. We have this audio track, it was playing together in sync, and then something came along and bumped the table, and now one of them slightly ahead or one of them slightly behind. It's the same basic principle here on what's going on, just with lasers and a whole bunch of fancy mirrors. So this change in position is of the mirrors itself is caused by the stretching and compressing of space as the gravity wave passes through us. And so ultimately, this arrangement gives LIGO a sensitivity of 10 to the minus 23 hertz in the 100 frequency band with a very modest laser, a 17-watt laser you can go out and buy on Amazon. It's not one of those crazy, oh, we built a multi-kilowatt laser to go and zap drones. No, this is basically a really powerful pocket laser that you could, by today's standards. So again, this is just a slight overview of just the general layout you have of a dual arm detector. You have two long arms with mirrors firing back to the beam splitter and a photo detector for the laser emitter. Nothing really too crazy fancy here. And with this setup, LIGO announced their first detection in 2016, but there were actually three different events that they detected during this observational run. And there are some primary things here that I wanted to talk to, just because it was interesting. And I'll have some other stuff. So kind of near the end point here of this. So I remember way back at the beginning, I talked about, hey, we have these two masses that merge. You'll see that we have this mass here representing the two merges. And then you'll see down here that we have a final mass, which you'll immediately notice there's a difference here of about 5 solar masses. So in this merger of these two objects, we lost close to 5 times the mass of the sun was converted into pure gravitational wave energy and possibly some other stuff. And we're able to determine other things like with triangulation with distance and peak luminosity, some other stuff. But just going back into the whole just tying this back to the earlier talk about like, hey, mass conservation of mass is a thing. It still applies. And so over as LIGO has continued to operate, we've detected a whole bunch of events. This is just a picture summarizing some of their detections to date, at least up to their 2020 observational run. So it's been about 6 years. I couldn't find one more recent than this, unfortunately, at least on their actual website. So the way you would read this chart is at the top left and the top right are the two objects, progenitor objects in the center and their masses. So we have 36 and 31. And then in the center, you have the object that it merged into and its resulting mass. And you can see that, we have various masses on here. The white dots are neutron stars, by the way. They may be very hard to see over the zoom call, but they're white dots here. So quite a lot of the stuff here. So, wrapping this up, this leads to some interesting questions. Ultimately, we're asking, why do we want to study gravity waves themselves? We built this thing, great. We found out they existed. We proved they existed. What do they actually tell us about stuff? Why do we need to keep studying these things? Why do astronomers want them? So the main thing, and I found conflicting evidence on this, and it might be partly from the sources I was working out were, slightly dated, and this has been answered in the time since. But one of the main questions was, do gravity waves carry energy? This maybe go a little bit of a misnomer because it says we're just bending in space, but there is like, do they carry energy? We kind of seems like it's a question that we're still kind of working that out. We're not wholly sure, or at least we are sure. And then I was just looking at dated sources. But nonetheless, it does lead to some interesting things. But notably, if gravitational waves do not contain energy, they would only be detected by interferometers. So great, we have that base covered if they do. The other main reason for studying these is we're hoping that they can help shed light on a path to giving the physicists' long-standing goal of uniting quantum mechanics and general relativity. As it's somewhat known, these two theories are incompatible with each other when it comes to dealing with gravity at very small scales. They do not work well. And so one of the large problems in physics is making these two theories actually compatible. This relates to another somewhat question in the theoretical particle space, asking, are gravitons real? These are a theoretical particle responsible for transmitting some aspects of gravity. So there's No, currently that's still very theoretical that in terms of like how do we actually detect them if they do exist, sort of thing. Another interesting thing is gravity waves help shed light on the evolution of black holes, and specifically supermassive black holes. So, as we're finding out with James Webb, if for those who have been following discoveries there, we've been finding these little red dots, which some very recent publications in the last 2 months have suggested that these are actually giant supermassive black holes surrounded in very hot gas very early in the universe. So we're like, hey, how do we get these? These shouldn't be here. So gravity waves themselves, they help shed light on exactly how the supermassive black holes would form. But it also helps us answer a question which is known as the mass gap of black holes. And this is specifically regarding stars which form black holes when they die, have what's at a certain mass range, stars between 65 and 130 solar masses, they just disintegrate themselves. They don't actually, when they go supernova, they don't leave behind a black hole upon their death. and so when this happens, we do know of black holes that are within this range. So we were like, how do we get these black holes between 65 and 100 solar masses if the stars that form them just disintegrate? So as we go back into this chart, you can see that we have a couple of black holes, like one here with 107, 175, 141, 102, that are all within this mass gap range. So it helps us. It's contributed there to helping us understand the evolution of black holes, which is important for helping to understand what the ultimate fate of the universe is, because black holes themselves will evaporate over time, and so it plays into that whole continuing understanding there. Yeah, but the other interesting thing is that gravity waves, because they are fluctuations in space and time, they are the one of the few things we know about, the other being neutrinos, that can be observed from beyond the cosmic microwave background. So the cosmic microwave background, as a reminder, is just this veil of microwave energy that we see in the sky that's left over from the cooling of the universe as it became transparent enough for light to travel. And so this is basically a barrier between the observable universe and the universe before light could transmit. So the way that we normally observe things with light, and which is our primary means for studying the universe, means that we can't see beyond the cosmic microwave background with any radio, optical, X-ray, gamma ray, any sort of that. But gravity waves aren't affected by this. They are bendings in space, and so this opens up an avenue for bigger detectors or more complicated detectors to be able to say, like, hey, what's going on in this area of the universe which spans from Big Bang to 300,000 or million, one of the two. This period of the universe between information and the recombination epoch, which is where light began to travel through the universe. And here are some of the three archive papers. Here are the main references that built the body of this presentation. There's more into those that I didn't want to elaborate on, but for those who want to screenshot this, or I can just post the links here in the chat, they're very interesting reads, and they're very digestible. Just skip the math. There's not a lot of math except for in, like, I think the second paper, but that's all like physics. You can just skip it. There's a lot of really good explanations. And that is that. That was a lot.
Yeah, very nice.
So questions, comments, discussion points. Let's go ahead and just throw these into the chat for people who want to go read them. Okay. So Tom's not asking questions when he was the one who started this presentation in the first place. I must have done a good job.
Well, you did an outstanding job. I can make a few comments on things I've read since then. One of the questions that I had asked last time is on the assumption that a gravity wave causes the mirrors at the end of the detectors, I guess you want to say, or the length of the tubes to expand or contract based on the fact that space-time itself is expanding or contracting when the wave comes through. Then that raised a couple of questions in my mind, and one of them was, okay, you've got light going there, but let's say that the endpoints of the tube are expanding away from each other. You would have just like we have redshift when we look at stars that are moving away from us, you would have a redshift in the light uh, in that tube. Now, if you're in that frame of reference, you wouldn't know it because your entire space time is, and you're expanding and contracting with it. So how do you detect it? Well, what I found out was that the trick is that, let's call it the speed of light, c as most people know it, remains constant. So even though the distance between the endpoints has changed, the speed of light has not. So the light arrives at a slightly later, slightly later time because the speed of light is the same always. And
Unless you're
so
not in
you
a
could,
vacuum.
well, right, uh, so
Cherenkov radiation is fun.
I'm sorry, say again.
Cherenkov radiation is fun.
um, so how is it detected? Well, one thing I read was that they detect the time of arrival of the light, and another thing I read was that they detect a change in the interference pattern between the two tubes.
They're out of phase.
Yep.
Say again, Doug?
That's the out of phase portion of what
the out of phase portion. Yes,
yeah.
That's exactly right. Yeah.
So, but on that note, you mentioned redshift, and it's worth noting that gravity waves also experience redshift because of the expansion of the universe.
Mm-hmm.
So Connor, I think, and I could be wrong about this, but you weren't sure about difference between dipole and quadrupole early in your presentation.
It's not that I'm not unsure about it. It's just I do not have the vernacular to adequately explain it at a level that other people can also understand.
Well, I think I can. Normal electromagnetic waves from a dipole source, like a north-south magnet or something like that, uh, are just polarized in two directions. Okay. I guess you could call it, the two directions go around, so that's why they call it circularly polarized, but it's polarized in just two directions. Okay, up, down, or side to side, and whatever, but it's like this or like this, and it varies as the wave propagates. I think a quadrupole source means it's polarized in four directions.
That's what I would thought too, in terms of just looking at the name of it. But
I don't know how you would how you draw the picture, because that looks like it would be very complicated. But
that was
I
one
believe
thing.
that's what we're talking about.
It's the way that it was described in the papers in terms of like how it was referenced and framed within gravity waves that made me unsure if that was actually the case. And then trying to actually figure that out led me into a whole bunch of really technical things. And it's like I didn't have time to actually sit down and digest all of
I
that.
think the reason it's very complex is we're not talking about a wave in three-dimensional space now. We're talking about something that's propagating in space-time. That makes everything a little bit more complex.
But again, it's a complicated thing. I didn't want to throw out an incomplete thing that I couldn't myself would raise more questions than I could physically answer in this meeting.
Yeah, I've seen those terms. I have not read anything about this, but when you mention quadrupole, my first thought was, oh, is it 4 dimensions? X, Y, Z, and T, the dimensions of space-time? I don't know.
Right. It's it's it also goes back into like me trying to want to avoid like, hey, this is electromagnetism, because you're then trying to say like, well, it's a quadrupole, so that it must be linked to some particle, which is I
No,
described here was not the case. So
no. I
I
think
didn't
it
want to
has.
muddle the
I think we're talking about how many directions it's
Yeah.
polarized in.
yeah. So again, it was a complicated thing. I didn't want to dive into this presentation
Yeah.
and confuse people more. It is a term. It exists. I just don't want to discuss about it. It hurts my head.
Um, I also raised the question of I still haven't gotten a good answer of, why is the speed of light constant? And I just recently listened to a Richard Feynman lecture, and what I think I got out of that is that the speed of light is not a property of light. It's not really a speed. I think he called it a conversion factor, actually, uh, that ties space and time together. And so, in effect, what we call the speed of light is really like the speed limit based on what space time can do. And so, it's not that light is limited, it's that space time is limited. And so, light can only go that fast. And so can gravity waves, which, as we know, also have no mass and, no particles or anything like that. But gravity waves can go the speed of light as well. And the reason is because it's a property of space time, which that conversion factor gives you the speed limit, as it were. So that's my best understanding of what I got out of the Richard Feynman
And all the
lecture.
years of knowing that the speed of light was finite, I've always just been like, it's because it's the only thing that doesn't have mass. And so I never really thought to deep ask her of like why, other than
Yeah.
the fact that photons don't have mass, about why is that speed of light the number that it exactly is. So that is actually an overall interesting question.
Yeah,
Um,
almost everything I've come across, the answer is basically, well, that's just the way it is. That's the
no.
way the universe works. 95% of the answers I came up with was that's just the way it works. And apparently Einstein even accepted that as well.
No, no, he did not.
Okay.
If you read some of Einstein's actual writings on the subject,
Yeah, I haven't read.
um, it has to do with the definition of simultaneity and some other stuff. When you start defining events, physical events happening in the space-time system, you go into the system of mathematics that get you there,
Mhm,
basically, the Lorentz transformation and so forth. And the constant velocity of light is a byproduct of that. It falls out of
mhm,
your transformation of coordinate systems that you have to use in order to define what simultaneous means.
mhm,
Certain things, certain properties of, like you said, space-time have specific definitions for simultaneity. I can never pronounce that word. Simultaneity. And when you go through the transformations to bring you that, it falls out.
yeah. Apparently, it also falls out of Maxwell's equations. The
That
I
wouldn't
don't.
surprise me one bit.
Apparently, if you solve a certain way, you end up with C, and it's like, wow, they didn't expect that. I don't know. Yeah, I also heard him mention other phrases like causality and things like that, and I kind of got lost there. So go back and read some more on that, but I that might be beyond my capability.
Cool. Um, so with that out of the way, um, gonna call it a night there, but there is some housekeeping stuff, so we'll stick
Okay.
around for a second.
Yeah, yeah. So Connor,
Let me
uh,
stop the recording here before you